Yeah, okay. Good afternoon. So let's wrap up our treatment of transport layer, and specifically we're talking about questioning the end-to-end principle, right? Rethinking the end-to-end principle. So just to summarize, the end-to-end principle is the idea that you consider, that you embed intelligence only at the endpoints of the network as opposed to the middle of the network. So your core routers don't do anything intelligent. They basically just do routing, and that's it. And this is evidenced by the fact that core routers on the internet only implement physical, link, and network layer. They don't even implement the transport layer and above because they don't do anything with it. They only do up to routing. Okay? And the end-to-end principle, you could argue, is one of the two or three, there's probably three characteristics of the internet that has made it so successful. So let's see if you guys can guess what they are. We've already encountered all of them. So I maintain, or I contend, there are three characteristics that contribute to the widespread, the widely successful internet, or the nature of the internet. So does anyone care to guess what they are? Three characteristics of how we do networking on the internet that contributes to its success. A bit louder? So end-to-end principle is one of them, right? Which is why we're discussing it and questioning it. So it's one of the foundations of network design, right? Which means you can scale up because your intermediate nodes don't need to do a lot. You can have routers processing at gigabits per second, right? If you had to have routers inspect every packet and do what I show on the left here, they couldn't operate at gigabit per second. Okay, so just in that thought process, to enhance our learning and our understanding of things, can anyone tell me what the other two are? What other two am I thinking of? I mean, this is all debatable. This is my opinion, okay? But still, I'm curious to know if you guys can guess. So end-to-end principle is one. The other two, we've already seen them. Yeah, who said that? Yeah, layering. So protocol layering. The idea that you can design a function by breaking it up into smaller sub-functions, right? So your big problem is solved by a bunch of layers, which are the sub-functions. And this allows a lot of things to happen, like debugging, code maintenance, code reuse, innovation. Right? If I want to build a better routing layer, network layer, if I want to implement a new routing protocol, it's very easy. I just plug it in. As long as the abstraction provided to the layer above and below is the same, everything will work. Okay, now, third. Anyone know what the third principle is? Third idea? Yeah, exactly. Statistical multiplexing, which in networking we call packet switching. The idea of on-demand usage of resources. So these are the three things, I think, foundations on which the success of the internet stands. Statistical multiplexing or packet switching, protocol layering, and the end-to-end principle. So it's a bit sacrilegious for us to be questioning the end-to-end principle. Okay? But anyway, you only learn by questioning, right? So the example that we gave was this first example, if you want to do fair allocation of resources, the brute force solution is to keep track. But that's very, very expensive. And I showed you a solution by Prabhakar's group at Stanford. His research group at Stanford came up with something called choke. What choke does is it looks at a router, the buffer in a router that's congested or getting filled up, and it's going to preemptively drop packets. How is it going to drop? It's the solution that they came up with that they showed works from an engineering point of view is to pick multiple packets, in this case 2 packets. If they match, throw it away. Because if you can pick 2 packets and they match, it means you're probably dominating the buffer. Okay, somebody asked a very good question last time. Can you prove this mathematically? I think it was you, Benita. And you can't. I mean, they did not prove it. But they showed that from an engineering point of view, this was enough. So this is an example of an intermediate router doing something. It's not that smart, but it's still doing something. It's dropping packets preemptively in a somewhat smart way. This is a randomized algorithm. It turns out that both examples I'm going to give you are randomized algorithms, but they are doing flow identification. And if you remember, the premise for questioning the end-to-end principle was to allow flow identification, because we argued the internet is turning into a network for transporting flows as opposed to transporting packets only. Of course, flows are made up of packets, but a flow has the same source and destination. Somebody asked me, what's a flow? A flow is just a set of packets that have the same source and destination. For example, if you're watching a movie, or if you're downloading a torrent or something, right? It's going to have the same source and same destination. Well, you're probably not downloading a torrent on campus, right? Because I think NUS, the network blocks torrents, right? So, does it? You wouldn't know. Of course you wouldn't know. Of course you wouldn't know. Because you've never tried it, right? Yeah. You know, there are valid reasons to download torrents. There are many valid reasons. Like if you want to download a distribution of an operating system or so on. Yeah. And in fact, I think there are actually places on campus that actually host these distributions and so on. So it's a bit counterintuitive that blocks torrents. Okay, anyway, so yeah, so this example was called choke, and it is a randomized algorithm, right? That's going to help us do flow identification. All right, and I'll give you another example. It's called elephant trap. Again, it's the same group. It's Prabhakar's group out of Stanford. They also explored this algorithm called SIFT. So the problem setup is as follows. So imagine you have this router here, and many flows are intersecting at the router. Now, if one of those flows dominates, now assume this is a FIFO buffer. So this router has a FIFO buffer. If you have a lot of packets from one flow, and very few packets from another flow, call those mice, you have elephants and mice, you can imagine that the mice are going to get trapped behind the elephants. Right? And you remember one of the sources of delay in a computer network is queuing delay in the router, while packets are waiting for their turn to be served. That's called queuing delay. Right? And you can imagine that if you are watching a movie, everything's fine, and then someone else whose flow is intersecting at that router is just looking at their bank statement. So they click on their bank statement and it just spins. Why? Because their packets are stuck behind an elephant flow. Right? Now, if there was a small delay in the elephant flow, right? Let's assume for the moment the application was streaming video. Well, suppose some packet in the upper right-hand corner got lost. Okay? So for, at 60 frames per second or 30 frames per second, one packet of one frame got delayed. You're not going to care. But the person who clicked on the bank statement is going to care. Right? So we care that there's a disproportionate, perhaps, depending on the use case, a disproportionate effect, quality of service effect on the mice. So what we'd like to do is to, again, see if we can identify these dominating flows and do something about it. But we want to do it without actually identifying the flow. And again, we're going to use a randomized algorithm. And we're going to, they proposed this algorithm called SIFT. Okay, what SIFT does is it's going to use this random sampling. Okay, so the idea is that a flow, so you flip a biased coin, like this coin, let's say, comes up heads 1/10 of the time, okay, and tails for 9/10, and a flow is sampled if one of its packets has a head on it, right? And then so roughly a flow of size X will get sampled 1/10 of the time, and most short flows will not be sampled, but most long flows will be, okay? So the idea is how we're going to use this sampler. We're going to use this sampler as follows, is shown at on the bottom. There's two use cases here. The top use case is the original network. I have a FIFO buffer with a size B buffer. and the server processes packets in a first come, first served manner. Okay? The bottom one is the modified setup, where you're going to, because you want to have a fair comparison, you still have a total of B spaces in your buffer. So I have two B by 2 buffers, and I'm going to have the sampler in front of them. And if I sample a flow, so I'm going to use a sampler to quote unquote separate short and long flows. Okay, and so the idea is now I have a short flow buffer and a long flow buffer. And then now I can serve these maybe in a round robin fashion, or I can even prioritize the short flows. Does that make sense? So I'm going to again do this. Now you might think, okay, sounds okay, but let's see the effect. Our metric here, because I was arguing delay, so our metric is going to be delay. Right? So let's look at delay. So this plot here, on the x-axis, it plots load. What is load? It's the amount of data I'm putting in on average. Okay, let's not worry too much about that distribution, but assume that as you go from left to right, I'm pumping more data into the network. And on the y-axis, I'm plotting the delay. And in this case, it's the overall average delay. And this is overall average over both short and long flows. And we see 3 curves here, but you can just look at 2, the blue. And the red and the green, they're variations of SIFT. Let's not worry about the variations. Let the blue and green be 1. Okay, so there's just 2 curves. Look at for example, you might look at the blue and the red. Okay, the blue is original. Now, notice that the y-axis is plotted in log scale. Don't lose that fact. Okay, it's on log scale. So, 1 tick is a factor of 2. Okay, so we see that when you average over all the packets, over all the flows, we see that the red curve has a significantly lower delay than the blue curve, right? By maybe almost an order of magnitude in the middle, like depending on the load. Okay, overall, like load going from here, as I said, you can think of this as the amount of data I'm pumping into the network. So this is understandable, right? Because, well, I'm prioritizing some of the short flows, right? So you would expect the delay to go down. Okay, so great. So this is overall. Okay, then you might say, okay, fine. Tell me what happens to the short packets, to the short flows. So this is what happens to the short flows. Again, let's ignore the red and green. Just focus on the red. Okay, so if you look at the red and blue, you can see that the average delay for the small flows is significantly smaller, which is good. That's the outcome I wanted, right? And it's like orders of magnitude, which is good. So the person clicking that bank statement is going to be happy. Well, depending on the amount of the bank statement, they may or may not be happy. But they'll be unhappy. At least they won't be unhappy about the delay in getting the data. Okay, so, all right. So this is good. Okay, so you might think short flows benefit, but maybe long flows get killed. So let's see what happens to the long flows. Right? Almost nothing. Right? In fact, again, I didn't do this. This is from the SIFT paper, so I didn't run this experiment. But in fact, it looks like for certain values of load, even the long flows benefit. I don't know if this is a statistical validity, you know, whether it's like has to do with like the amount of running time or not. But you can roughly say there's almost no impact on the long flows, right? Which is good because, well, there's a lot of packets from the long flow. And just because a few of them get delayed, when you average, it's going to be like nothing. Which is kind of what we thought. You know, if it's streaming video and you miss a few packets, you're not going to be too concerned. So, right, so this is good, right? We see that this random sampling, again, allows us to do maybe not explicit, but implicit flow identification, and allows us to do something a little bit smart. And you could argue this is not that smart. But anyway, it's smarter than what it was doing before, because it's dropping packets. Now, like I mentioned this last time, IPv6, the network layer protocol version 6, right now we're using version 4. Version 6 has an explicit flow identification field. So at that time, a router will just be able to go into the flow identification field and do something different. Okay? So just to let you know that this is before IPv6, right? People were thinking about this already. So it's important enough of an idea that it's built into IPv6. Okay? This idea of flow identification. So I think that's all I want to say here. Okay? That perhaps some of these principles that we start off with, that we take as unquestionable, as written in stone, maybe it's worth questioning them, right? Of course, one should understand why they were there in the first place, which is why I told you I believe that the early days of the internet owe its success to 3 principles, one of them being the end-to-end principle. But maybe as things evolve, right, we should know why they were there and why they might be questioned, right? Many of you might be working for next telco, right, and maybe designing the next generation network. If you are, hopefully now you have the basis on which to ask good questions. All right? That's the whole point of doing this questioning. All right. Any questions? Very good. So I want to, with this, we wrap up our transport layer. Okay? And the next topic is going to be the network layer, which is layer 4, which does essentially routing. Okay? Or finds a path from source to destination. Okay. What we're going to do now is we're going to ask this question, because we just got through transport layer, which is about end-to-end reliability. Okay, so this is very similar to our question, our first why question, which was what? What was our first why question? Does anyone remember? Who remembers our first why question? Yeah, why do we use IP and MAC address on the internet? Okay, so this is our second why question. Why do we, wait, why is this not showing? Didn't I just resolve this issue? This is irritating. Oh, that's why you guys couldn't see what I was doing. No one, why did no one call me on it? I'm here typing away. You're going to silently wait while I talk to myself? You guys got to speak up. Okay? I don't know why this is like this. Is it? Okay. So the question is, so why do we have reliability at both layer 2 and layer 4? So, yeah. Maybe somebody wants to take a cut at it? First of all, do you believe me that there's reliability at both layers? Who says yes? Who says no? So you say yes or no, or you're not sure? You didn't raise your hand. Sorry? So let me ask again. When I ask a question, give me a response. This is not a passive, it's not exercise in passive listening. Okay? If I ask a question, especially a binary question, this is a set of all possible answers. You have to choose one of them. Okay? If you don't, I'm going to ask you if you understand me or not. That's fair, right? Look, I understand maybe in your other classes you can sit and listen and not have to do anything. I told you that's not the case here. So, do you believe that the reliability exists at both layers? If you think no, that does not exist at both layers, raise your hand. If you believe it exists at both layers, are you a no? Did you say yes or no? No, but did you raise your hand just now? No, so if you believe it's no, raise your hand. If you say yes, raise your hand. Okay, so why maybe I ask you, why do you think it exists at both layers? No, this lady here. Don't worry, you're next. Yeah, but why do you think it exists at both layers, layer 2 and layer 4? Like, why did you say yes? Yeah. Okay. So you're saying that there are mechanisms that happen at hop by hop, and things not hop by hop. Why did you say yes? Not network layer, right? Transport and link. Layer 2 is a link layer. Layer 4 is the transport layer. Network layer is layer 3. Okay? So again, why do you say yes to that question? Okay, there's mechanisms for checking errors. Yeah, that's correct. But network layer also has a checksum. Does that mean network layer also has reliability? Okay. Well, you could argue that the checksum is reliability, but there's no real action taken based on it, right? Yeah. Actually, that's the third why question. Why the checksum at so many layers? Okay, but anyway, yeah, so there is reliability at link layer because you talked about retransmissions at the link layer. And there's reliability at the transport layer because we talked about retransmissions at the transport layer. So the fact is reliability does exist at both layers. So the question is, what is the difference? So what is the difference? Anyone can tell me? What's the difference in the reliability at the two layers? Yeah, correct. So which one is hop by hop? So layer 2, which is the link layer, is So actually, the short answer, the difference is what I call the scope. Okay, layer 2, and by scope we mean like over which like view or domain does it apply. So link layer is hop by hop, while layer 4, which is the transport layer, is what? Yeah. Okay? What this means is, when you talk about link layer, if A is sending to B, then A is responsible. No, if A is transmitting and B is the next hop, then A wants to make sure that B got the message. Yeah. So A wants B to get the message, and B wants to let A know it got the message. In end-to-end, you have A, B, C, D. Let's say D is the destination, A is the source. A wants to make sure that D got the message, and D wants to make sure A knows it got the message. That's what we mean by scope. Okay? So which layer? Okay, so this is good. Okay, so we have the difference is scope. Okay, now so how about the next question? Anyway, has this got anybody thinking? Why do we need? Our original question is still there. let me highlight it so we don't forget it. Yeah. So anyone want to see if you can answer the highlighted question? Yeah, Max? Uh-huh. Okay, yeah. So I like the way you're thinking. So anyone else want to share their thoughts? Thank you, Max. Anyone else want to take a cut at what? Yeah? Faster retransmission. If what? Yeah. Okay, good. So I like that. That's great. I think it's similar to what Max was saying, right? Anyone else? Did you want to say something? Yeah. Okay, so I'm hearing that it's more efficient, right? It's faster. Okay, good. So I like the way all of you are thinking. So the next question I want to ask is something that Max answered. What type of reliability do we actually want? So, Max, I know you answered this question, so just hold off for a sec. So, what type of reliability do we actually want? What's the end goal? Yeah, when A wants to send to a destination, A sort of doesn't care if anyone in the middle gets it. A just cares that the destination gets it, right? So we actually want, not actually, maybe we say, oops. Okay, we really want end-to-end reliability. The source just cares that the destination has got the data. Okay? So we want end-to-end reliability. Okay? So now, the question is, and then I think if our goal, what did I do? Hang on. So if our goal is end-to-end reliability, then why not? Okay, so we want end-to-end reliability, so which means that if we implement end-to-end reliability, we are good, right? Okay. But if we implement hop-by-hop reliability, then are we good? Are we good or not? Given we know what we want end-to-end. So if we implement end-to-end, we're good. But if we only implement hop-by-hop, then are we good? Oh, hop by reliability, hop-by-hop. So let's play a game then, okay? What's your name? Yeah. Matthew. And what's your name? Priyanka and? Spell it for me? Tomo. Matthew, Priyanka, Tomo. This is the route, okay? Me, Matthew, Priyanka, Tomo. Okay, that's the path. I'm the source, Tomo's the destination. Suppose that the link between me and Matthew is secure because I'm implementing hop by hop. and the link between Matthew and Priyanka is reliable, and the link between Priyanka and Tomo is reliable, then doesn't it look like the link between me and Tomo is reliable? Right? So it seems like if you implement hop-by-hop reliability, then, let's try this. Then maybe things still work. Right? I'll put a question mark here, because we're almost sure, right? So do you believe it? That if what I just described, if me to Thomas is reliable, Thomas to Priyanka is reliable, Priyanka to Tomo is reliable, therefore me to Tomo is reliable. So hop by hop, so the claim, the hop by hop reliability gives us end-to-end reliability. Okay, which means that what? We don't need to implement both, right? And based on all of the arguments that Max, Benita, and what's your name? Spell it? Pranati. So the Max, Benita, and Pranati gave, based on those three arguments, which one should we implement? Yeah. Should implement hop by hop, because he said it's more efficient, right? It's faster. Right? Faster recovery, it's more efficient. I'm saying, yeah, this is the route. Right? My network layer has given me a route. Yeah? Link layer is going to make this route reliable, this link reliable. And Matthew's link layer will work with Priyanka's link layer to make sure that link is reliable. And Priyanka's link layer and Tomo's link layer will ensure that link is reliable. So routing doesn't come into play here. If you change routes, then you can talk about on that new route. Okay? So it looks to me like what you guys are saying is we should do away with transport layer reliability, because, well, it's what we want, but layer 2 reliability gives it to us and it's more efficient. So does everybody understand the more efficient argument? The more efficient argument is as follows. If let's say you have A here and the destination down here, and let's say it goes through like 100 hops. Actually, 100 hops is a lot. I think the maximum diameter of the internet, somebody can Google it for me, is like 60. Right? I think any 2 points on the internet are separated by at most 60 hops. So my 100 hop thing is fictional. Okay, but let's say you have a 100 hop network. Okay, a 100 hop route. Well, if that packet, I think this is what Max and Benita and Pranati, right? We're trying to say. If it gets, let's say it gets down to the 99th node, and the last hop is a wireless link, and the packet gets lost. Well, if you had end-to-end, you'd have to start at the source again. And these 99 hops that it went through were wasted. Whereas if you can recover at the link layer, then, yeah, so that's the efficiency part of it, right? Correct? Okay. So head scratching. Why do we, like all your logic seems to indicate that we should only implement hop-by-hop reliability, like layer 2. And we should drop layer 4. But we just spent the last 2 weeks. So our last 2 weeks was a complete waste. Now, I probably wouldn't have spent time on it if it was a complete waste. So maybe if we assume that I'm somewhat rational. Yeah? Okay, so then I'll drop retransmissions at the, yeah, so I'll drop whatever, yeah, I mean, you said, I mean, you're right, given that we committed to a protocol, yeah, you might be able to find some things I still need to do, but maybe I could do them at layer 2. Yeah, I mean, you make a good point. But I want to now I want to look at the big picture. And yeah, maybe if you allow me to gloss over your detailed but correct point. Okay, so we'll gloss over that for a minute. Is that fine? Yeah. Why? But you can still sequence them, right? There's no reason why linked layer cannot sequence packets. Why? Why can't the I don't know. When I send it out, I order it, yeah. I don't think that's so much of a problem. I mean, it's a problem to be solved, don't get me wrong. But I don't think it's unsolvable. The big question is, can we do it with end-to-end reliability, meaning layer 4? Yeah. Yeah. No, but if you have buffer overflow, doesn't linked layer take care of that? So our premise is a linked layer is reliable. If A wants to send to the next hop, it will happen. That's the premise. Like we have to restructure that, right? Yeah, I mean, that's another point that you're making, right? Yeah, I mean, we have to restructure our protocol stack. Yeah. I think it's not insurmountable. You guys are raising valid points, but what you're saying is that if we took our current stack and just hacked it, like I said, things would break. But you'd fix things. Like if I want to remove linked layer reliability, I try to fix things. And I think you can. So I just want to make sure we're on the right. So how about this? Let's write this. Then so we turn it into a question. And the claim is that hope by hope. Right? This was the claim. Hop by hop implies end-to-end. And I want to say to me, it's still a question mark. And if you know why I'm dwelling so much on this, what's your best guess? This was a flaw in the argument. Okay, so you cannot do away with end-to-end because hop by hop does not guarantee end-to-end. Now you got to figure out why. Okay, but once we figure out why, then we know we have to implement end-to-end because that's what we want. And we implement by hop because of the efficiency reasons. Okay, so this is our unanswered claim. But if the claim is false, then we need to implement end-to-end and hop by hop is for efficiency, right? So we don't have to recover all the way from the source. Okay, so hop by hop is for efficiency, end-to-end is because that's what we really want. But all of this hinges on our claim. If the claim is true, actually we can do away with layer 4. We have to do a few hacks to figure out some of the really correct and valid points all of you mentioned. Max, Matthew, and this gentleman here. What's your name? Prince. Prince, Matthew, and Max mentioned some things that are all valid. Okay, so now, Do you agree all we have to establish is this claim? Or establish the validity of the claim? Does hop by hop imply end-to-end? You guys all were very quick to say yes. So anyone know the flaw? So the answer is actually no. So anyone know what the flaw in the argument? Me to Matthew, Matthew to Priyanka, Priyanka to Tomo. All those links are reliable. Why does that not give me end-to-end to Tomo? Yeah. Yeah, or the nodes might break. Yeah, so the point is, so let's take from me to Matthew. Matthew getting the packet from me, which is what link layer reliability guarantees Matthew gets my packet. What it does not guarantee is that Matthew forwards the packet. Right? It only guarantees my packet made it into Matthew's buffer. And then what does a packet have to do? It has to queue in the buffer, right? It's a FIFO queue. It has to wait for the packet to eventually be served. What if in the middle of that Matthew decides to get up and go to the bathroom? I mean, if it's Matthew, or if he's a node, his power gets turned off, or there's a malfunction, or I like to imagine you're like a sensor in the forest, and an elephant comes by and steps on the router before it forwards the packet. Right? So, but the key idea is that link layer reliability does not mean that I'm guaranteed that the next hop will actually forward the packet. Okay? So that's why you need to, so this claim is actually false. So the claim is false. Yes. So does hop by hop? The answer to this question is no. Okay, good. So, all right, before we go, I have set up a little assignment for you all on Canvas. If you look on, actually somebody can look on Canvas. On Canvas, there is, actually it's the same question. The same question, why do we have, because I think it's good for you to try to articulate it in your own words. Okay, maybe I should just like delete this. Okay, so the question is this, but actually I give you the guiding questions. Okay, so there's a file there that you download. I password protected the file because I'm just experimenting with Canvas. I wanted to see if I could incentivize you all to come to lecture. So I'll give you the password now. The password is Singa 2024. SINGA 2024. Okay? Everything, no, just everything lowercase, yeah? What? What's your question? What? What? Sorry? You want me to undo? It's okay. Just I give you the questions, right? So if you look at if somebody can download the file, make sure that you can get it. And I gave you the password, and then you just enter it's an assignment. So I'm just trying to see how Canvas works. So I set up an assignment with a file upload that's encrypted, and you should see the questions. I give you all the guiding questions. You just need to logic your way through them. But I think we talked about it long enough that you should all know, right? Max, you have a question? Yeah. It's just Singa 2024. SINGA 2024. Okay? Due by the end of the day. Okay, so just upload your answer. But again, the point is not the right answer. I want you to think through. Like, really think through the guiding questions and make sure you kind of get the logic. Okay? And if this works out, I'll do more of these. I'm not going to grade it, but I'm going to see that you've done it. Yeah. Now, we'll be looking at it. If you upload rubbish, then I'll know. But the point is, if there's a sincere effort, I'm not going to say you're right or wrong. Yeah. I mean, I wouldn't say that if you upload a really funny joke and you make me laugh, that I won't accept it. I might. If you make me laugh, I might accept your joke. But it depends on my mood, obviously. Okay, good. So let's just try this as an experiment. Yeah, I mean, I think it's good for you to close the loop on things we do in class. Right? That's the whole point, right? Is that I spend a lot of time on discussions in class, and sometimes students come back to me and say it's a bit too open-ended. But I feel like that's how you really learn. So I'm willing to take the feedback if you guys think, I mean, if you think there's a better way we can do stuff, let me know. But I feel like some of these open-ended questions and getting you to ask questions and think is on the way to actually learning something important. Okay, thanks everyone. I'll see you on next Monday. We'll talk about network layer.